Hello everyone. Today our group will be presenting on a very important topic in differential equations, linear homogeneous and non-homogeneous differential equations. But what is a differential equation? Simply put, a differential equation is a mathematical equation that involves derivatives. It is an equation in which the independent and dependent variables and the differential coefficient of the dependent variable with respect to the independent variable are involved. In other words, it connects how something is changing with the quantity itself. Now, among the different types of differential equations, we have linear differential equations. These are equations where the dependent variable and its derivatives appear only to the power of 1 and they are not multiplied together. The general form looks like this. Now here is the key part. If the right hand side f of x is equal to 0, we call it a linear homogeneous differential equation. However, if it is non-zero, it becomes a non-homogeneous equation. Let us now focus on homogeneous equations. This type of differential equation represents the natural behavior of a system, how it evolves on its own based solely on its internal properties. There are no external forces or influences involved. To make this more concrete, let us look at an example. Here d is equal to d by dx. We will now form an auxiliary equation where we replace d with any variable m to get an algebraic equation to find the roots. So m square minus 3m plus 2 is equal to 0. We get m as 1 and 2. Solving the auxiliary equation gave us the values of m which are used to build the general solution of the differential equation. Because there is no external input or non-zero function, the general solution to a homogeneous differential equation is made up entirely of the system's natural response, which is called the complementary function. Thus, we get the solution as y is equal to c1 e to the power x plus c2 e to the power 2x, where c1 and c2 are arbitrary constants that depend on the initial conditions. The graphical representation of the solution would look like this. The blue dashed line is e to the power x. It grows steadily but not too fast. The orange dashed line is e to the power 2x. It grows much faster because of the bigger exponent. The green solid line is one possible combined solution. The important point is that the real solution is always some mix of these two basic curves. If the coefficient in front of e to the power 2x is larger, the curve shoots up faster. If it is mostly e to the power x, the growth is slower. So the shape of the solution depends on how much of each curve is present, which is set by the initial conditions. Now, based on the nature of the roots, the complementary function and thus the general solution will be of the form c1 e to the power m1x plus c2 e to the power m2x and so on, where m1, m2 and so on are distinct. For real and equal roots, we have c1 plus c2x plus c3x square into e to the power x, where we have three equal roots. For imaginary roots in the form of alpha plus I into beta, we have e to the power alpha x into c1 cos beta x plus c2 sin beta x. Finally, when we combine case 2 and 3, we get imaginary and equal roots. Now let us move on to non-homogeneous differential equations.
Now let's talk about non-homogeneous linear differential equations. The idea is simple. A linear differential equation is called non-homogeneous when the right-hand side is not zero. The general form of a non-homogeneous linear differential equation looks like this. There are four key cases of non-homogeneous linear differential equations. Let's understand each of them with an example.
This case involves a non-homogeneous term of exponential form. If the right-hand side is e to the power ax, substitute d with a in the operator f of d. If f of a is not equal to 0, the particular integral is of the form 1 by f of a into e to the power ax. If f of a is equal to 0, then we use the derivative and multiply with x. Let's look at an example question. Here, after finding the complementary function in the same way Nithya explained, we look at the right-hand side, which is sin hx. Here we use the formula e to the power x minus e to the power x by 2. Since f of a is equal to 0, we use the derivative and multiply by x. We combine the particular integral from both values and add it to the complementary function for the final answer. In case 2, f of x is equal to sin ax plus b or cos ax plus b. Here we substitute d square with minus a square, as long as f of minus a square is not equal to 0. If it is, we use the derivative and multiply with powers of x as we did in the first case. Let us consider an example. D square plus d minus 2 is equal to sin x. Here, the value of a is 1 as the coefficient of x is 1. Substituting this in the denominator, we get 1 by d minus 3. We then rationalize it and get the final answer as minus 1 by 10 cos x plus 3 sin x. Moving on to the third case, f of x is equal to x to the power n, when the denominator is of the form 1 plus or minus phi of d, we bring it up to the numerator and expand using the binomial theorem. This is an example showing the same. Case 4 is where the non-homogeneous term is a product of the exponential and another function which can be either trigonometric or polynomial. Here, you add a to the operator d by dx and solve as in the previous cases. Here is an example to help understand it better. We hope you have understood non-homogeneous linear differential equations clearly. By following these structured techniques for each type of non-homogeneous terms, linear differential equations become much more manageable. Each method targets the specific nature of the right-hand side to build a particular integral, ensuring all possible cases are covered.
Thank you, Nithya and Annika. Now that we've understood both linear homogeneous and non-homogeneous equations, let's bring everything together. First, let's do a clear comparison between the two. So what does this table right here tell us? A homogeneous equation is like observing a system in isolation. We only see how it evolves naturally without disturbance, whereas a non-homogeneous equation is more realistic for daily life because it shows how the system behaves when it is influenced or disturbed by outside forces. Now, let's expand on some applications in real-world scenarios across different fields. For our first field, we have physics, where think of a guitar string. If you pluck it once and leave it, the vibration you hear is the natural response of the string. This is modeled by a homogeneous differential equation. But if you continuously bow a violin string, the sound is sustained because there's a continuous external input. That is modeled by a non-homogeneous equation. For our second field, we have economics. So imagine the economy growing naturally based on population and resources. No outside push. That's homogeneous growth. But if you imagine the government giving out subsidies or stimulus packages, these act as external inputs that alter the system, which makes the equation non-homogeneous. Now, coming to our third field, which is engineering and more specifically electrical circuits. When a capacitor discharges on its own, the equation describing the current is homogeneous, but when we connect an external power source, say an alternating current, it becomes non-homogeneous because the circuit's behavior is influenced by that input. For our last field, we have biology. For this homogeneous case, we can take the example of the natural decay of a population without any migration or disease. But if we add an external factor like regular food supply or a vaccination program, then the growth or decay is modeled by a non-homogeneous equation. So, what have we learned so far? Homogeneous equations give us the pure natural response of a system, how it behaves if left alone, whereas non-homogeneous equations
show us the real world response. Because in life, systems are almost never isolated. There is always some external force, some input or disturbance acting upon them. The distinction between homogeneous and non-homogeneous differential equations highlights the existence of two fundamental layers of reality. The first being the intrinsic laws that govern a system in isolation, and secondly, the external influences that shape and modify its behavior. Homogeneous equations describe the intrinsic behavior of system, the natural vibration of a string, the autonomous growth of an economy, or the decay of a population. Non-homogeneous equations, by contrast, account for external influences such as sustained resonance in music, government policies in economics, or medical interventions in biology. Together, they demonstrate why differential equations are a powerful framework for understanding both natural laws and the ways external forces shape them, a parallel that also reflects the balance between our inherent nature and our responses to the world.